Hi guys, this is Mr. Holly. We are looking at lesson 2 of our probability and statistics unit. Today we're going to be talking about how to estimate probabilities by collecting data, and what we're really doing is trying to make inferences about how likely something is to happen based on our experiments or experience. Sometimes you'll hear this called experimental probability. That's kind of the idea that we're looking at today, is as we do things, as we do experiments, what assumptions would we make about the likelihood of things to happen. So, example 1 is about a carnival game. The spinner spins twice. So if it was my turn, I spin it twice, and I win that turn if I get more than 5. So here I've got a spinner, and I would place that on, on the number wheel here, and I would spin. And on my first turn, I got a 1, so it's not looking very good for me to get 5 or more here. I have to get a 4 in order to succeed. And if I spin, I got a 2. So on my first turn, I lost. I only got a sum of 3. On my second turn, I would spin it, and I got a 3. Alright, I should win this time, I hope. And a 2. Good, I win on this turn. Continue this experiment for 15 turns, and you are going to make a judgment call about how likely it is you think it is to succeed. Now, you can actually do this at home on your own. Give me just a second. I've found an online resource for you. Alright, so now on the screen you should see a wheel instead of my document camera. So you can find wheels like this online. You're just going to search for, I actually think what I searched for on this one was a board game spinner, and I was able to customize this to be 1 through 4, so I customized it 1 through 4. So I'm just going to click it, and I got 4 and 2. So I just put those numbers down, 4 and 2. You can do this at home. We'll try to put a link in the Canvas page for you to go to an online spinner so that you can actually do the experiment yourself and you would get your own results. Okay? I'm going to finish this experiment. I'm going to pause the video and I'm going to get the rest of my numbers. Okay, so I've gone through and I have finished all my turns. I've spun 15 times, I guess a total of 30 spins, but 15 turns. And I was able to win 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9 turns where I won. Okay, so let's answer some questions about this on the back. Out of the 15 turns, how many times was the sum greater than or equal to 5? I got 9. Obviously, if you do this activity on your own, you will have different answers. Okay. What sum occurred most often? So I could look and see. I assume 4 or 5. 5 occurred 1, 2, 3, 4 times. 4 occurred 1, 2, 3, 4, 5 times. And 6 was 1, 2, 3, 4 times. So it was number. Sorry, I got twisted up in all those numbers. Number 4 occurred 5 times. 4, and it occurred 5 times. Which sum occurred least often? Interestingly, I did not get 2 or 8, which were possible, and 3 only occurred 1 time. So I got 3 occurred 1 time. If students were to play a lot of games, what proportion of the games would they win? Explain your answer. Well, what we would do is to compare the number of times we won to the number of times we played. So we won 9 out of 15 games, right? So if we were to think about how many students would win, they would win 9 out of every 15, or that could be simplified to 3/5. Or we could talk about it, we just finished percent, we could say 60% or 60 out of 100. These are all acceptable. Based on our experience, we can assume students would win about 60% of the time. Now, if you spun and you only won 5 times, then based on your experience, you would assume that people would only win 1/3 of the time. If you won 10 times, you would assume people would win 2/3 of the times. Your ratio will reflect your experience. Okay? So this is not, we are not looking at the exact or theoretical idea of probability right now. What we're looking at is based on your experience, what can you assume? So we won 9 out of 15 times. I can assume that people win 3 out of every 5, or 9 out of every 15, or 60 out of every 100. Name a sum that would be impossible to get while playing the game. Well, a sum of 9 would be impossible, because you spin it twice, the maximum amount is 4. 4 plus 4 is 8. That's the highest I can go. What event is certain to occur? A sum between 2 and 8. It's certain that I will get some number between 2 and 8. All right. Let's look at the next page. When you're spinning the spinner and recording outcomes, you are performing a chance experiment. You can use the results from a chance experiment to estimate the probability of an event. In the example, you spun the spinner 15 times and counted how many times the sum was greater than or equal to 5. An estimate for the probability was the number of observed occurrences and the total number of observations. So this was the times we won over the times we played. Like, we're comparing those two things. And in our experience, 9 out of 15 games, we won. Based on your experiment of playing the game, what is your estimate for the probability of getting a sum of 5 or more? Well, for us, that was the win. That's what it involved, winning. So it was 9 out of every 15 turns. We think the probability is 9/15, or 3/5. Based on your experiment of playing the game, what is your estimate for the probability of getting a sum of exactly 5? Let's go back to our data. How many times did I get exactly 5? 1, 2, 3, 4. So I would assume that 4 out of every 15 times is a good estimate for the probability of getting exactly 5. Right. Let's look at another example. Example 2 is about animal crackers. It's another experiment. It's about a student that bought this huge jar, those huge bags or whatever, of animal crackers. And he reaches in, and instead of counting them all, he just grabs a sample. And he pulls out 20 randomly chosen crackers, and he counts them and finds the following information. There were 2 lions, 1 camel, 4 monkeys, 5 elephants, 3 zebras, 3 penguins, and 2 tortoises, for a total of 20 crackers. So we're going to make assumptions based off of this sample to see how many of each we think there is in the bag. So, based on our sample, what is the estimate for the probability of selecting a lion? Well, a lion, there are 2 of them out of 20 observations, or 20 experiments there. So 2 out of 20, which is equal to 1/10, or 10%. We could even write that as a decimal. The likelihood is 0.1. If you remember yesterday, you did chance probability on a scale of 0 to 1. Chance is 1/10. What is your estimate for the probability of selecting a monkey? Well, 4 monkeys were selected out of 20 crackers, which is the same as 1/5, or 2/10, or 20%. This is the likelihood of selecting a monkey. What is your estimate for the probability of selecting a penguin or a camel? So either one. There were 3 penguins and 1 camel, so penguin or camel. 4 of the crackers were either a penguin or a camel out of 20. Are you catching what I'm saying here? Or means both of these would be an acceptable outcome. Either one of those, either or, is an acceptable outcome. We had 3 penguins and 1 camel, so the chances of picking one of these there were 4. It happened 4 times. So again, that's 1/5, or 2/10, or 20%. What is your estimate for the probability of selecting a rabbit? Well, there were no rabbits chosen. So 0 out of 20. Probability is 0. It is impossible. Is there the same number of each kind of animal cracker in the large jar? Based on our experiment, I would have to say no. But it is a small sample size. It is only 20 out of a huge jar. It is impossible to truly get an understanding of the ratio of the crackers with only choosing 20. We would really need to look at a bigger sample size. In fact, we might need to look at several bags and over and over to see how much of each, to see if they were actually proportional, like the same number of each. Now, that being said, you would also have to think about what is the likelihood that they would get the exact same number of animal crackers in each bag, even if they made the exact same number of each animal in the animal crackers. What's the likelihood that when they were going into the bag, the exact same number of each animal fell into the bag? Because there's probably some assembly line process, right? So essentially what we're trying to pinpoint here is the idea that this is happening by chance, and that the likelihood of it just working out perfectly like that is very slim. So I would say no, and based on our experiment, the answer is no. So there's probably not. If a student randomly selected another 20 animal crackers, would the same results occur? Why or why not? The answer to that question is also no. There are 20. They picked 20 crackers out of a bag that might have hundreds in it. So if you picked a whole nother 20, what is the likelihood that those 20 would be exactly the same? And it would be very unlikely. If there are 500 animal crackers in the jar, how many elephants are in the jar? Well, there were 5 elephants out of 20 selected crackers. So we could estimate that if there was a total of 500 crackers selected, this is 20 times 25, right? Is that right? Sorry, my brain locked up. That's definitely 20 times 25. We could also scale this up times 25, and that is 125 elephants available. We could also think about this as an equation, a proportional equation, a percent equation, right? 5 out of 20, so 25% of the bag is elephants. So you could say the part of the bag that's elephants is equal to 25% of the whole bag, which is 500 crackers. So the part that is elephants is 125. Connect that back to proportional relationships and percent. All right, so there is experimental probability. This is not always true. It is just taking what we have learned and making our best guess based on our experience. So we're making a guess based on experience. All right, thank you.